Hello, this is Stefan again from schristoph.online. Today we'll talk about my latest blog post, The Beach Test. Why big neural networks stop getting stuck. It started with a question I hear constantly from engineering leaders. Why do our models have to be so enormous? And doesn't bigger just mean it memorizes more? The answer, it turns out, is hiding in a bucket of sand. The idea came into focus listening to Mathieu Villard, a theoretical physicist on the podcast Machine Learning Street Talk. VR's home turf is glassy and granular matter, window glass, suspensions, and yes, sand. He spent years studying what makes a pile of grains flow or lock up, then pointed that same lens at deep learning. Start with the sand itself. Loose, dry sand flows because each grain has room to rearrange. But pack the grains densely enough and something changes. They lock into a force-bearing network and the pile turns rigid enough to hold a steep wall. Physicists call the onset of that rigidity a jamming transition. Now picture training a neural network as a ball rolling downhill on a lost surface. Via's group showed this surface has the same kind of transition as sand. With too few parameters, the landscape is rough and full of holes, and training gets stuck in poor spots. With enough parameters, it develops broad, flat valleys, and gradient descent can almost always find a way down. Here's the picture on the left. The under-parameterized surface is rough with many little pits, and the ball gets stuck partway down. On the right, the over-parameterized surface smooths into one broad valley, near zero loss, and the ball settles at the bottom. The paper that formalizes this is here. Its language is careful. A phase transition, analogous to the jamming transition of granular media, marks the boundary between the regimes where fitting can or cannot be achieved. You might reasonably ask, is this a real explanation or just a cute metaphor? VR is careful here. He is not claiming a network is a bucket of sand. He's claiming the two problems are structurally analogous. Both are constraint satisfaction problems with continuous degrees of freedom, and that shared structure is why the same kind of transition appears. This reframes what all those extra parameters are for. The instinct is to see billions of parameters as wasteful slack. The physics says the opposite. The extra parameters are what turn a jammed, holy surface into a flowing one. Size buys trainability, not just capacity. There's an important caveat, and the work spells it out, right? At the transition, generalization actually gets worse. There's a cusp where classical overfitting lives. It improves again only as you push well past the threshold. So the place you want to be is comfortably over-parameterized, not balanced on the edge. But if a model has far more parameters than training examples, why doesn't it just memorize the data? The surprising answer in the setting studied most carefully is that generalization tends to arrive before memorization. Early in training, the model discovers the structure of the data. Only much later, and more slowly for bigger datasets, does it start pinning down individual examples. Now, is that a universal law? Honestly, no. This is a result about over-parameterized diffusion models learning structured data, not every model everywhere. But within that setting, it just memorizes intuition. Finding structure is the fast thing the model does first. So what is this structure the model finds early? VR's hypothesis is that real data is approximately compositional, a hierarchy of parts within parts. A scene is made of objects, objects of features, features of edges and textures. Depth is the tool that matches that shape when the data actually has it. This diagram shows the idea. A single class at the top branches into high-level features, each feature into sub-features, and those into raw tokens, like edges or characters. A deep network learns this by peeling off one level of the hierarchy at a time. The group made this concrete with what they call the random hierarchy model, a synthetic task built with exactly this parts within parts structure. Here's the paper. In it, they show depth, let the network exploit that structure, and they estimate how much data it actually takes to learn. The most forward-looking part is about what you ask the model to predict. Today's dominant recipe is to predict the next token. VIA's candidate for doing better is to predict your own internal latent representation of the data instead. The idea behind architectures like JEPA and data to VEC, he argues those introspective methods are far more sample efficient. This is the JEPA paper, a joint embedding predictive architecture. It's one concrete instance of predicting in latent space rather than at the raw token level. For those of us who help teams choose and deploy models, This cashes out in two stances. First, when someone asks why we need such a large model, you have a principled answer. Size buys trainability, not just memory. When you pick a foundation model on Amazon Bedrock, treat that size as a feature you're benefiting from. Second, take latent prediction and world model approaches. Seriously, if a future model needs far less data to reach the same capability, that reshapes the economics of fine-tuning and data acquisition. I leave the last word to Via, because it landed with me. He said, if you take risk, you should make mistakes. If you never make mistakes, maybe you're staying on the beaten path. Some of us want to explore the jungle, and in the jungle, you can be wrong. So dig the hole, build the castle, and the next time someone frets that a model is too big, tell them about the sand. Thanks for listening. I hope this was helpful. If so, you can reach out on LinkedIn directly or head to my blog at schristoph.online. Let's keep in touch. Take care.